Okay, so we will talk about augmentation of data structure. Suppose augmentation means instead of having a data structure from the crash, we want to make use of some existing data structure and we want to add some extra information there, that is called augmenting, and we want to take help of that data structure for our problem. So, we will talk about two problems in this lecture. One is dynamic order statistics, that means OS select, so we know the select, we know the order statistics, it is basically finding the ith smallest element in a given input, and there our input is, this is a static, input is fixed, I mean we are not changing it or we are not inserting or deletion in the input. So, but here S is dynamic set, S is dynamic set, that means we are allowing the insertion, insert and deletion. So, we are allowing these two operation in S. So, that way it is a dynamic set. So, S is a dynamic set which is so now we want to perform this in this problem in this S, that means we want to have this which will give us the ith smallest element in S, the set S which is having say n element, okay. But this S here is dynamic set. So, it is any element can be inserted in S or any element can be deleted in S from S. So, how we can maintain this, how we can have a data structure for this problem. So, we will take help of some existing data structure, then we will do some extra, we will put some extra information and then we will use that. So, that is called augmenting. So, we will use the red black tree as our underlying data structure, because this is a balanced tree. Since this is balanced, so we want to use this as our underlying data structure and we want to give more information for our solving this problem. What is this? So, this is the key value and we want to keep the size. Size means the size of the tree rooted at this node, that is the size of the tree. So, and this is the key value. So, this we want to, this is the augmenting, we have using the existing red black tree and there we are putting this extra bit of information there, storing the size of the tree. Okay. So, let us take an example. Okay, suppose this is our tree, these are the values, key value C, P, A, F, let us make it little big so that we can have this other bit of information. So, this is N, this is Q and we have another two nodes. Again, I want to make it little big. This is D, this is H. Okay. And we obviously have the nil. So, this is a red black tree, we can put the color on this tree and we have nils over here and the size of the nil is convention is we put it 0, okay, while we implement this. So, now what is the size of this? So, this is 1, 1. So, each node is having two field, one is key and one is the size of the tree rooted at this. So, this is the size 1, 1. So, size will be what? Size will be size of left subtree, size of right subtree plus 1. So, this is 2. Now, size will be 1 again here. So, size of left subtree. So, this is the size of, so size of this is basically, so this is the formula. Size of a node is basically size of the left of x plus size of the right of x plus the node x itself. So, this is basically 3, 4 and this is 3, 1 plus this is 3. So, this is 5 and this is 1, this is 1, this is basically 1 plus 1. So, this is 3 and this is basically 5 plus 3, 8 plus 1, 9. So, this is the our new data structure, which is basically a red black tree, but we have an extra bit of information which we are storing the size of the tree rooted at that node. Okay. So, now if we have this data structure, now how we can do this OS select. So, we want to so we want to so this is our tree. So, what we do, we will just take the, so this is the root of the tree. So, x is the root of the tree, or we can just take tree and this I. So, tree is formed. OS select is basically we first take the x as the root of the tree and then we defined as k is basically size of the left of x plus 1. So, can you tell me what is this k represent? K is basically size of the left. So, k value of this is what? Size of the left of x plus 1. So, this is 6. This is, we can check nothing but the rank of this node. That means, in a sorted order, if we sort this element, then the position of that node is basically rank, that is the k. Because if you do the in order traversal, that will give us the sorted one. So, this will all the will be printed. So, this is the size of the left subtree 5 plus 1. So, this is the basically, this is nothing but the rank of x. Now, we are looking for ith smallest element, means we are looking for an element whose rank is I. So, now the code is similar. If I is equal to k, what we do? We return the x, else if I is less than k, what we do? We have to look at the left part of the tree, then we call the same OS select with the left of x with the I, same I. This is the same code as we discussed in our select. Okay. Now, here if not, else if I is greater than k, else that means I is greater than k, then what we have to do? We have to go for the right part of the tree, then we return OS select right of the tree, right of x, but with the I minus k smallest element. Okay. And we can have a checking whether so we can just so this is the I minus k smallest element in the right part of the tree. Okay. So, this is the code. Now, if we for this example, suppose we want to find out the fifth smallest element, suppose I is equal to 5. Suppose this is our input, I is equal to 5, fifth smallest element. So, this k is so I is equal to 5. Now, rank of this node is, this is the sixth smallest element. So, this is not. So, now I is less than 6. So, we have to go into the left part of the tree. So, we will call this recursively on this subtree, left part of the tree with the same value of I. So, now if you do that, Now, again we calculate this. So, this is basically now we are looking for I is equal to 5. Now, if you consider only this tree, now what is the rank? Rank is basically 2 for this node in this tree, subtree. So, now I is greater than 2. So, we need to go for the right part of the subtree with the I value I minus k. So, 3. Now, we are looking for third smallest element in this subtree. Now, what is the rank of this? Rank of this is again 2. So, this is k, sorry, this is k. Rank of this element in this subtree. So, now we now I is greater than k. So, we have to go for the right part of this tree with I is equal to 1 and the rank of this is k is 1. So, we will return this. So, this is the fifth, H is the fifth smallest element. Okay. So, now this is the OS select. Now, this set is dynamic. So, that means any node can be joined at any point of time and any node can be deleted. So, while joining the node, we need to follow the insert algorithm for red black tree insert. Okay. So, there we need to check, we have this is a augmenting of the red black tree. So, we have to check how we can change this extra bit of information while we are doing the modifying operation. So, that we need to verify whether this is easy or not. So, suppose we want to insert, say here we want to insert a node which is k. So, k is basically less than m, we will go here, k is greater than c, we go here, k is greater than f, we go here. So, we will put k over here. Now, the same way, so this is 1. Now, the same way we will just change this. Now, the change how much time it will take, we need to see the while we do the modifying operation. So, suppose this is the situation, we have E and we have a 16 over here and we have C, we have 11 over here. Now, we say this is the size. Now, this is the size of the this. Now, if we perform the right operation on C, the C will come up and E will come down. Okay. E will come down. Now, C will be having this 7 and E will be having this 3 4, because this is alpha, this is beta 3 4. Now, how to change these values? Now, this is basically this plus 1. So, this is 8 and this will be basically 7 plus 8 plus 1 16. Okay. So, this is also can be done in constant time along with the changing with the pointers. So, this is no problem here for this for maintaining this extra bit of information. Okay. So, this is the even the for the recoloring also we do not need to spend extra time on this. Okay. So, this is the augmenting the data structure. Okay. So, now we will talk about this another problem which is called interval search. Okay. So, interval search, it will be basically will form the interval tree. So, the problem is we have given some interval time intervals, say we have given say time intervals like 7 10 say 5 11 say 17 19, we have some given interval 4 8 5 11 say 15 18 and say 22 23. So, these are the suppose this is the this is the interval, this is if this is I we denote this interval at I, this is the low of I. So, lower end point and this is the high of I. So, we can just write h and h of I, L of I, and this is the h of I. So, low end point, high end point. Okay. So, now suppose our query interval is this, say we want to find, we have a given interval I, say I is say 9, 10, okay, or say 15, 17, 15, 18. Now, we have to, this is a given interval, say these are the interval, there are n intervals, and we have a given interval I, and which we need to find out what are find out a overlapping interval with this. So, we need to find out overlapping interval with I. So, who is overlapping? So, this is 17. So, this is overlapping, this is also one, we can just report only one. So, this is the problem. So, we have to report this interval 17, 19, and this set is dynamic set. So, we have a set of intervals which is set S. S set is basically set of intervals, there are n intervals, and this set is dynamic. So, any interval can join at any point of time, any interval can get deleted at any point of time, and the query is, we have given a interval, query interval, and we need to find out a interval, an interval which is overlaps with the query interval. So, that is the problem. So, to solve this problem, we will use we need to have a data structure. So, basically we will do the data structure augmentation here also. So, we will use the red black tree as our underlying data structure, and we will do some, we will add some extra bit of information there. So, basically we will use red black tree here also, red black tree, and by keyed the left end point or low or left end point as a key. Okay. We have an interval. So, when we make the tree, we have to have a field which is called key field. So, that we can use that value to make this binary search tree. That key value is the left end point, and what we know, what we do the augmenting, this is the interval, and here m we put, m is the maximum value in that tree rooted at that node. So, m is the, so this is m of x, m of s is the largest value or maximum value in the tree rooted at x, that is the m. Okay. So, let us draw the tree which we have for our this given interval. So, 17, 19, then this is 5, 11, this is 22, 23, we can make it little big. So, this is 4, 8, these are the interval we have given, and we need to form a red black tree, 7, 10. Okay. So, now we need to and we have the nils over here. Now, we need to fill that another field maximum element. So, how we define the max of x? Max of x is basically maximum among these three numbers. So, this is basically high of x, high end point, high of x, or max of left of x, or max of right of x, whichever is the maximum, it will be that maximum. So, this is basically 10. So, if you have tree rooted at this, 10 is the maximum in that tree rooted at this, and this one will be the 8. And what about this one? This one will be the maximum of left sub maximum this, and there is nobody over here. So, 18, and this will be maximum between this and this. So, this is 18, and this will be again 23, and this will be maximum between 18, 23 and this. So, this is basically 23. Okay. Now, we can just for a practice we can put the color, so that we can have a red black tree. So, which color we give? So, we can put this red, and we can put this also red. Now, we can check this is a red black tree, and the key we use this left end point as the key value. So, you can just 17 5 is, so it is satisfying the binary search tree property. So, 5 is less than 17, you can just easily verify this. Okay. So, this is our new data structure, not very new, it is basically augmenting of the existing data structure red black tree. So, now we want to see if we have this how. So, we are this is a dynamic set. So, we are allowing the insertion and deletion. So, we want to see how much time we are spending for doing the modifying operation. If we have to insert a node, then we have to change the color, will not take time, we have to see the restructuring, the rotation operation. So, if we look at that, suppose this is the interval 11 15, and this is say 6 comma 20, and say this is our alpha, this is our beta. Suppose we have a 30 over here, we have a 14 over here. So, this will be 30, and say this is 9, this is the gamma. Now, if we want to do a right rotate on this, so this will come there, this will come down. So, this will basically, so we have a tree over here. So, 6 comma 20 will go off, and this will be coming down, and we have this will be hanging here 30, and these two will be hanging here 14 and 19, and then this value is basically maximum of this is 19, and this value will be maximum of this. So, this is also a constant time. While we are changing the pointers, we can do this. So, this modifying operation will not take much time. So, that sense we are safe. Now, we have to so this we can very much use. Now, we have to look at the search code, how we can, if we have a given interval, how we can have a overlapping interval. So, that is the interval search, and this tree is called interval tree. Okay. So, let us write the pseudocode for interval search. Suppose we are searching this interval I. Okay. So, in a we have given a tree, we have a set S n element, and we form the tree, this new tree, which is basically a red black tree with some more bit of information, and this is the input. So, this is the I, we are trying to find the I is an interval. So, I is having low of I, high of I. So, this I is an input, and we are trying to get the interval which is overlapping with I. So, what we do? We first take x as a root of this tree. Now, we check. So, x is an interval, sorry x. So, x is an interval. So, x is having low and high, low of x, high of x. Now, we have to check whether this interval is overlapping with x or not. If it is overlapping, we will return x, stop. But if it is not, how to check it is not overlapping? So, if I is completely here, I is completely here means if the high of x is less than low of x, if the high of I is less than low, or I is completely there, that means if the high of x is less than low of x. So, that we have to check, then there is no overlap. Okay. So, if while x is not null, and this is the checking for non overlapping. And low of x, low of I, if it is greater than I of x, and or low of this is x, low of x, small x, sorry, low of x is greater than I of I. If this true, either one of this, then that means not overlapping. This is basically I and x are non overlapping, do not overlap. So, then we have to go down. So, that means what we need to do now? If they are not overlapping and it is not a nil node, then we have to check. So, this is basically we have to go either left or right. Now, if left of x is not null, is not nil, and low of I is less than m of left of x, then we go for the then x is equal to left of x, else x equal to right of x. Okay. So, that means, so suppose we are looking at, so this is our x, now this is our m of left of x. Now, if m of left of x, if this is if low of x is less than this, then we will go for left. If low of x is greater than this, so suppose m of this is less than low of I. So, that means we are looking for a overlapping where low of I is greater than this, that means low of I is greater than m of left of x. So, that means the subtree rooted at is maximum value is less than low of I, then there is no question of going to the left part, then we are going to the right part. So, that is this case, else case. If the maximum value in the low of x is less than left of x is less than I, then we will go to the right part, because there is no question, there is no overlapping, because the interval itself is greater than this. So, we will go to the right part of it. So, this is the code. So, what is the time complexity of this code? It is basically log n. So, now let us take an example, quick example, how it is working. Okay, so the same example, same tree. Suppose we have this tree 17, 19, 5, 11, 22, 23, 4, 8, 15, 18, 7, 10. Okay, now we fill this 10, 8, 18, 18, 23, 23. Suppose our query interval is 14, 16. Suppose we are trying to find out the overlap interval with the 14, 16. So, we check is there any overlap with this? No. Then we go to the, we check this with the low of this. If the low of, so this is, so then we go for this subtree, left subtree, because low of this is less than maximum value. So, we should have something over here. Now, this is our x. Now, we go look at the left part of this. This is 8. Now, our interval is starting from 18. So, 8 is the maximum in this subtree. So, there is no question of going there. So, we will look at there. So, when you look at there, we compare with this. So, this is has no overlap. Yeah, this is having overlap. So, 14, 15 and 18. So, this is having overlap. So, we will return this one. So, we will return 15 and 18. So, this is we return. Okay. Now, similarly, you can check with the I is equal to 12 and 14, which is having no overlap. So, it will reach to the nil node and then we end there. So, this is the code. So, this is the has time complexity log n, because we have to maximum we are traversing the tree from root to the leaf. So, the height is balanced tree. So, the height is log n. So, the time is log n. Thank you.